Howdy, folks. My name is Arul Verma. I'm going to be your other teaching instructor for this semester for CS Information Honors alongside with Neil. And this week, I'm going to be talking about Rust basics. So the goals for today are to talk about the basic data types and the syntax in Rust, what mutability is in Rust, control flow, which is basically conditionals and loops, and if we can make time for it, we'll talk about file input and standard input. So let's start by talking about what data types are. Data types are the method by which we tell the compiler what type of data it's reading. These are built into the compilers. Users can access these data types with predetermined keywords. And there are two types of data types, scalar data types and compound data types. Compound data types are the tuples and arrays. We'll talk more about these next week, but all you need to know for now is that they store multiple pieces of information, and they always store the same type of scalar data type. Otherwise, let's talk about scalar data types. Scalar data types are your integers, floating points, booleans, and characters. So what are these integers, floating points, booleans, and characters? Well, let's talk about them. Numbers in Rust can be expressed in two different ways, integers and floating points. Integers are always used for whole numbers, so there is no decimals in integers, and they will always round your value down. If we were to do the calculation 15 divided by 2 in integers, we would get the output 7, because the 7.5 that we get would then be cut off the decimal and give us just the integer value, the whole value, which is 7. On the other hand, if you wanted to get that decimal value, you would be using a floating point number. Floating points are always used for decimal representations, and they allow you to have more control over your number, but at the same time, they're not always very precise. Floating point error in the compiler is essentially when the compiler has too many decimal value data points, and the value you're seeing as output, say you get 7.5, might actually be a tiny bit off from what the computer is actually storing. You may actually be storing 7.499999998. So there are some solutions to this problem, but all I'm trying to say is that floating point numbers are generally very finicky. So you may always want to use integer numbers for calculations, or you may have to learn to adapt for floating point error and how to tolerate that in your code. So let's talk more about how we declare our integers in Rust. So if you look at the top code, you'll see that we have int x equals to 5. And if you're familiar with C++, this will look very familiar, because this is how you declare an integer in C++. In Rust, it's slightly different. Rust doesn't use the int keyword to declare an integer. Instead, you use i32 as your keyword. And i32 is a default integer size, and you can use that for whatever types of data you're trying to store, usually for integers. However, Rust also allows users to use other types of declarations, which are i8, i16, i32, i64, i128, u8, u16, u32, u64, and u128. All of the U data types are unsigned, so they store the same amount of data as your integers. However, they are non-negative, so they'll always be shifted up. And I'll go more over that on the next slide. All of our signed data types are just normal integers, and what these different numbers mean is just the size or the range of how many values our integers can store. Again, more on that next slide. So before I move on, I want to identify some very important things that Rust does that are different from other programming languages. Whenever you're creating a variable, you want to use the keyword let. Let is the keyword that lets the compiler know that it's looking at a variable that's storing some sort of data that it needs to store in permanent memory. So whenever you're making that variable, you always say let variable name, and then you say equal to whatever. And you can notice that I said both of these are correct. In one of them, I do declare the type of my data, and the other one I don't. So Rust compilers are very good at filling in the blanks, and they're very thorough. So you don't have to say i32. The compiler will fill that in for you. However, generally it's considered better practice to declare what type of data you're storing in your variable. And you do that using the colon method. You say colon, and then you put your data type after. And this allows the compiler to know what type of data type it's looking at, and it'll store it in memory accordingly. However, it's perfectly fine to do what is on the right, which is let x equal to 5, and this code will run. So if you want to do that, that's perfectly okay. Just be careful, because it will make your life a little bit tricky when debugging, because it's a little hard to understand what is stored in what data. So some important things to note from the previous slide is the let keyword. It's very important because that's how you declare a variable. And in the future, you'll be using it a lot. So make sure you take note of that. The other things to notice is the sizes that I talked about earlier, the 8, 16, 32, 64, and 128. So this is essentially just to tell the compiler how much space it needs to allocate for that variable. So this can be used to make your code much more efficient, which isn't necessary for this class particularly, but it is a useful tool to know and can be used later in life if you continue to code in Rust. So the memory that is allocated is dependent on what this integer is here. So for example, on I8, we would go, the range of the integer's possible values would be -2, 8 to the power -1, 2 to the power 8 minus 1, minus 1. And if you run those calculations, you'll say I8 has a range of -128 to 127. This is to the power -7. This is to the power 7 minus 1. So unsigned ints, on the other hand, they can't be negative. So what happens to that other space they have in data? So they just shift over. So a U8 would go from 0 to 256, or 255 actually. But otherwise, they work functionally the same way as integers. So next we're talking about floating points. Floating points are your decimal value storage methods. Integers are used for whole numbers. Floating points are very specifically for decimals. I don't know if briefly I mentioned floating point error, which is essentially that when you have a floating point in your code and you're storing it in memory, say I want to store 15 divided by 2, and I get 7.5. It may not always be true that what the computer is storing for 7.5 is equal to the actual 7.5 value. The compiler generally has some sort of error tolerance that it has for data storage. So if you try and store 7.5, you may end up storing 7.500000001 or 7.499999998. There's a certain level of tolerance that the compiler allows for floating points because it's possibly perfectly accurate with decimals. So because of that, floating points can be a little bit finicky when you're using them to code. It's sometimes an issue, and you need to be aware that floating point error exists and that you have to adjust your tolerance for that because this data you're storing may not actually be the data you think you're storing. Other than that, floats work just like ints do. There are two types, F32 and F64. Your F32 is your single decimal value precision. So this means that generally you'll be rounding to the first decimal value, so 7.5, for example. And that's the default value that if you don't declare your variable and you just use let, then you'll get a F32. F64 is your double decimal precision, and that just means that you have more decimal points on the end. And generally, F64s are, you have to declare them explicitly, and otherwise they work the same as ints and F32s, but F32s will serve all your purposes in this class. So let's talk a little bit about mathematical operations. So Rust supports mathematical operations when assigning to variables and also just doing them in general. And Rust will automatically assign types to variables whose types are not specified, as I talked about. If you just use the let keyword, things will be fine. So the other key thing to note is that Rust doesn't support intertype operations. So you cannot do operations between a float and an int. And you cannot, and if you do an operation between two floats, the result will also be a float. If you do an operation between two ints, the result will also be an int. And if you wanted to do like cross-value operations, you must do some sort of typecasting, which is something we'll go over much later. And if you want to read more about it, feel free to. But just know that the typecasting is the method by which cross-type operations are done. So let's take a look at a little bit of code in which we go over some operations being done. And it's pretty much the same code that we saw earlier. I'm just going to run this so you guys can take a look and see how it works. Which ones are going to be floats, which ones are going to be integers. And yeah, let's run it and see what happens. So we can see that our sum is 15. That makes sense, 5 plus 10. Our difference is 91.2. That also seems fine. Product seems okay. Quotient. And now we see the first instance of where floating point error could really realistically occur. We can see that we have so many decimal points that if we try and store this value and like check for equivalence, we may be off because the computer has so many decimal points, it's just showing us a certain amount of those decimal points. So we need to be a little bit careful with floating points in the future, and especially in your code, be aware that this could be a problem. Now, another interesting one is floored. We can see that we did 2 divided by 3 and we got 0. And logically, 2 divided by 3 is not 0, 0.66666. But because of how data types work, this is an integer result, and 0.6 truncates off or cuts off all of the decimal values, so the output result is just 0. And finally, we have remainder. Remainder also makes sense. You use the percentage sign to represent a remainder or a modulo function. which is just if I do get a remainder, what would the remainder be when I divide by this value? And 3 makes sense. That's a logical output. So let's go back to our slides. So next, let's talk about characters. So characters in Rust are a little bit different from other languages. So we have both indent types for characters and strings, but string declaration and usage is a little bit more complex than the topics I wanted to cover in this video. So let's talk more primarily about characters. Characters are the way we store single alphabetic pieces of data and when I say alphabetic, I don't mean alphabet specifically. You can also store 1, 2, 3, 4, 5, 6, any single digit information in a character. The only caveat is that when you're storing that information, you must keep it within single quotes, not double quotes, specifically single quotes. So characters are represented with the keyword char, C-H-A-R, char, however you want to say it. I know that's a point of debate. But you always want to use that declaration for that explicit type annotation for those type of data. And Rust is a far more powerful character type than other languages do. In C++ or Python or even other languages, characters are usually limited to the ASCII symbols, which are numerics, are characters, some special types like our special characters like exclamation marks, slash, but typically they have limitations. They can't do emojis, for example. Rust is a lot more powerful. This is because in other languages, characters are typically 1 byte long. So there's a limit on how much data they can store. And in Rust, characters are 4 bytes. So they're slightly larger, but at the offset for this slightly larger amount of storage, they can store special things like emojis or special characters. And if you go online, there's like a whole list of what the denotations are for emojis and storing emojis. One way, of course, is to just paste the emojis in your code, as you can see that there's done in this code right here. And we have heart-eyed cat being a variable equal to the emoji of heart-eyed cat. So characters are very interesting, and you're definitely going to be playing a lot with them on your first homework. So look out for this in the emoji storing value. So now let's talk about Booleans. Booleans are your true-false data type. There isn't much about them because they're very similar to how you'd expect true and false to work. They're used in control flow to evaluate expressions. They store true and false. They're 1 byte in size. And one thing to note is that they're all lowercase, which I know is like something that's different to this language compared to other languages. But there are many languages out there that use all lowercase as well. So it's not too special. The data type keyword is bool, B-O-O-L. So when you want to declare a Boolean, you use the bool explicit type annotation. So now let's talk a little bit about mutability. Mutability is something that's very unique to Rust and how it protects its data. So the way Rust works is when you declare a variable, it's not intended to be changed. The computer doesn't plan for it to be changed at any point in time. So all of those variables that we looked at previously, let t equals true, let f equals false, c equals z, sum equals 5 plus 10. If I wanted to go back and say, oh, I want to change these values from what they originally were, I want to get, let's say sum equals 10. Now I want sum to equal 16 instead of like what it was before. So Rust inherently prevents me from doing that because it wants to make sure that my data wasn't accidentally edited by someone. So say I had my 2 integers. If I try to edit one, let's say they're right next to each other in memory, I might accidentally edit the second one. This is something that you'll go over in future classes, of course. But the point is that Rust wants to protect against those type of issues where other pieces of data that aren't intended to be edited are edited by accident. So what Rust does is different from other languages in that it makes your declared variables inherently immutable. They can't be changed. So this means once you declare a variable, it's assigned forever to its value. So if I said let t equals true, throughout the lifetime of my program, t means true. I can't change that. But sometimes in code, you want to be able to change a variable. So Rust has an inherent way to do that, and that's through the keyword mut, M-U-T. And that just means mutable. So it lets the compiler know that, oh, I might want to go back and edit this value. I don't want this to be fixed. And the way you do that is you say let mut variable name equals to whatever the data is supposed to be inside that variable. And of course, you can have your explicit type declaration as well. So here we can see a little bit of code in which we have a mutable being used. And let's just see it in running as well. I have it over here on the side, so we can just test it out. So here we can see the exact same code that we had in the slide earlier. And if we run it, we'll see that we could actually edit the data in our X. It went from 5.2 to 6.7. Now, just out of curiosity, what would happen if we remove the mute? What did Rust tell us that there's an error? Would we get the same value twice? So let's try it out and take a look. And we can see we get an error. It tells us that we can't assign a value twice to the immutable variable X. So this is what I mean in that when you have a variable in Rust, you need to be able to declare it, or to be able to change it, you need to use the keyword mute. So be aware of that and make sure to look out for that. So now let's talk about conditionals. So conditionals are your if conditions. They're the ways you're telling the computer that, like, if a certain condition is met, then do something. And those are using the keywords if, else if, and else. All your conditions are evaluated using a Boolean expression with Boolean logic. So an example of that would be, is integer x equal to 3? And the way you do that is through these type of special syntax ways. So once I declare your variable let number equal to 3, you can check if your number is equal to 0 or not equal to 0 using these special expressions. For example, not equal to, I'm sure that's familiar. Equal to would be the double equal sign. And you can have greater than, less than, greater than, equal to, and less than equal to, of course, as well. And all of your conditionals are if, else if, and you can have an unlimited number of else ifs, and then your else. All the contents of your condition, so if something is true, then everything in the then portion must be within curly braces. And everything in the if portion does not have any braces around them at all, or any form of like parentheses. So you can see we have some versions of that code underneath. So we have let number equal to 3, if number is not equal to 0, print number was something other than 0. And the ones on the bottom I'm going to go over right now. So if conditions are fundamentally expressions themselves. So you can do some creative things with them. For example, let number equal to if condition, which in this case is true, let it be 5. Else, let it be 6. So, and if we print this value, this code will run and it'll give us number is equal to 5. This is because the if condition is evaluated as if it's a line of code, and then it's just kind of removed, it's ignored, and we just get let number equal to 5. But the one on the right here, you'll notice it has, of course, both these don't have explicit type declarations, but this one has both of these being integers. This one has one integer and one string. So if we try and run this code, you'll actually get an error, because to do this type of expression assignment, Rust requires that both of your assignments that you're going to make must be of the same type. So this works because both this 5 and this 6 are integers. But this does not work because this is an integer and this is a string. So Rust will sense that these are not the same, so it doesn't know how much data it has to allocate for x, or for number beforehand, which will throw an error. So next, let's talk about loops. So there are 3 different ways to implement loops in Rust. That is the loop keyword, the while keyword, and the for keyword. The loop keyword is used to repeat indefinitely until a break statement is reached. So you won't really be using this in this class. And if you're interested in how loop works, you can definitely ask in Discord and we'd be happy to go over it with you. But for the most part, we're not going to be covering it because it's not essential and it's not very that important. On the other hand, the loops you're going to be using a lot more in this class are while and for. So while loops, you can see one demonstrated on the left. We say let mute number equal to 3, while number is not equal to 0, print number, and then number minus equals to 1. And this kind of, if we run that code, you'll see that we go from 3 to 2 to 1. And once we get to 0, that code never executes. It exits that code, so we print left off. So they're used until a certain condition is met, and we don't exactly know how many numbers. So this is a very simplistic example where we know that we want exactly 3 different digits to be printed. But in the future, if you don't know exactly how many times you want to run through your loop, you'd be using a while loop. In contrast, for loops are typically used when you know exactly how many times you want to go through some sort of iteration. So for example, if we look at the code on the right for I in 1.4. And we'll take a look at this code in a minute. I'm going to run it with you. But I want you to try and take a second to guess what that code would exactly do. So before I run it, just take a second, pause and think about it. Would it print 1, 2, 3, 4? Would it print 1? Would it print 1, 2, 3? Would it print 2, 3, 4? Okay, so let's run it and see what happens. So we get 1, 2, 3. This is very important to know that Rust, this left-hand side is inclusive, but this right-hand side is not inclusive. So when you're using a range kind of like this, so you want to find like a range of values, the left-hand side is included, the right-hand side is not. And this is particularly important when accessing like, when doing an iteration through an array, essentially, and indexing, because in that case, you have to know what your right side index has to be, or otherwise you might have a memory error. So the other types of loops are enhanced for loops. So they're, instead of like going index-based iteration using like the dot dot format, by the way, if you use parentheses 1 dot dot 4, that would give you a list of all the values from 1 to 4. I forgot to mention that. But say you don't want to do that. Say you want to go through each element individually and you don't want to index through your elements. So A is an array here, and this is kind of the syntax for it. We'll go more over next week, as I said. But for each element, variable element in A, so it would access 10, then 20, then 30, then 40, then 50. We could print what that value is. And this would print 10, 20, 30, 40, 50. So this is another way to iterate through all of the elements in your array without having to go through index-based iteration. So that's about all we have for today's lecture. Some quick reminders. There is Rust extra practice and query learn for you to go over and kind of practice on Rust. And if you're interested in trying out and looking through like the textbook itself and kind of learning a lot of these concepts through more formal documentation, I advise you to go to the Rust textbook online. And it's the Rust programming language textbook. It's the documentation. And this week, we kind of went over chapter 3. Other than that, it's important to know that the homework one is being released next week, so get ready for that. And the add drop deadline for this class is tomorrow. So if you have any friends who are interested in joining, feel free to invite them, but make sure they have the class in their UIUC self-service by tomorrow. So yeah, I think that's about all we have time for. I'm looking forward to talking to you guys next week.